We were discussing about thermal expansion in the previous session, and we saw the mathematical relation of thermal expansion, linear expansion, surface expansion, and volume expansion, etc., in terms of what was called the coefficient of linear expansion or coefficient of surface expansion, etc., etc. So let's start today with a couple of more situations to do with thermal expansion. Okay, so what we had explored about principle of thermal expansion, that fractional change in length is equal to coefficient of linear expansion into change in temperature. Fractional change in any area or surface area is equal to coefficient of surface expansion into temperature change, where beta for a given material is always 2 times alpha. And similarly, fractional change in volume is gamma into delta T, where gamma becomes 3 alpha, or you can write it as 3 by 2 beta or whatever, like this. Okay. So in terms of applications, let's start with another example problem. So what we have today here is a situation like this, let's say, where we have like a triangular frame, but it is made of metallic rods, okay, which are pivoted or which are hinged at the ends. So this is a metallic triangular frame which is made of 3 thin metallic rods which are hinged like this at the ends or at the vertices. So these two rods are of length L2 and are made of particular metal which has coefficient of linear expansion alpha 2, whereas this one is of length L1 and it's of made of metal which has coefficient of linear expansion alpha 1. So this is triangular frame of 3 metallic rods hinged at the vertices, let's say P, Q, and R. So in this, two of the rods are identical. So rods PR and QR are identical, of metal which has coefficient of linear expansion 6 into 10 raised power minus 6 per degree C, and length equal to 12 meters at a temperature of 25 degrees C. Whereas the rod PQ is of metal which has coefficient of linear expansion unknown, but length equal to, let us say, 16 meters at T naught equal to 25 degrees C. Now it is observed that this height of the triangle, this is independent of temperature. Whether we increase the temperature or decrease the temperature, the shape of the triangle will change because of thermal expansion or contraction. But the height of this triangle from the vertex R, that height will remain independent of temperature. So find the value of alpha 1, that is the thermal expansion coefficient of the rod PQ, if the height or altitude h of the frame is independent of temperature. Okay, so just try this question out. Thanks. Okay, anybody else who's got the answer? I'm going to start discussing it, so please send me the answer if you have come up with something. So first, let's try and understand the question, how this is happening exactly. So let us say at some particular time, the shape of this triangular frame is like this, with the three metallic rods hinged together. And as we've seen that these two are of lengths L2, which is of length L1, and it's a different material, whereas these two are of same material. Now suppose we are to increase the temperature of only the two sides which are of L2. If only their temperature is increased while this one's temperature is kept the same, then the frame would tend to rotate about its hinges, because these two would expand, okay, in length, and the frame would tend to become of this kind of shape. Okay. So that would happen if only these two ones lengths were changed, whereas this one's length remained constant. If this became L2 plus delta L2, so expansion of these two would tend to increase this height. Okay. Similarly, if only the top one were expanded and the other two of this equal lengths L2 were kept at the same shape, then the opposite effect, the height would tend to decrease. So if from this original shape, what we did is we expanded the length of the base of length L1, keeping the other two the same, then thermal expansion of this one would result in, okay, this kind of a situation occurring. The height would tend to decrease. Okay, but what we want is that when all three's temperature is changed, all three rods temperature is being changed, then at such a point of time, all three rods stretch, but in such a way that the altitude does not change. So this is the situation that we are looking for. That if at the original temperature, the shape of the triangle is like this, and we increase the temperature now, so the shape of the triangle changes to this. Changes in such a way that the triangle expands in length for all three sides, but the altitude remains the same. This is the situation we are looking for. This is the situation we are looking for. Okay. So for this to happen, there has to be a relationship between alpha 1 and alpha 2. So let me verify that relationship, okay, how that will happen. So basically at okay, T naught, L1 was given to us, L2 was given to us. Okay. So the height is square root of L1 square by 4 plus L2 square. Okay. Where I'll just substitute the values of L1 and L2 given, which was 16 meters and 12 meters respectively. Okay. Now at any new temperature, T naught plus delta T. So if delta T is a positive quantity, the shape should change like I've shown over here. L1 prime, the new length of this one will become this, okay, which will become L1 into 1 plus alpha 1 delta T. And this one's new length will become this, but the altitude should remain the same. So the same value of H should remain equal to this quantity here. Okay, so we should be able to connect these two and from that find a relation between alpha 1 and alpha 2. Oh, sorry, my mistake. Yeah, it's the hypotenuse. Yeah, yeah. The formula is L2 square minus L1 square by 4. And here that will become L2 plus delta L2 whole square minus. But yeah, so the idea is that individually these lengths have changed for the hypotenuse and the base, but the perpendicular, which is the height, that is remaining the same. Okay, so all we have to do is compare these two equations now. This is equation 1 and equation 2, and of course substitute these values here. So for any delta t, this statement 2 should be correct. Okay, so comparing 1 and 2, okay, I'll get that h, which is square root of L2 square minus L1 square by 4, should be equal to L2 plus delta L2 square minus L1 plus delta L1 whole square by 4. So if square root of A is equal to square root of B, we can square both sides and say that A is equal to B. So now here I will substitute this as L2 into 1 plus alpha 2 delta T. Alright, so far it's just simple algebra. Now at some stage we are going to use approximation. So I'm coming to that stage. Okay. Binomial approximation, that is. This is the case now. Now I'm going to use this, that 1 plus alpha 1 delta t square, we will approximate it as 1 plus 2 times alpha 1 delta t. And similarly 1 plus alpha 2 delta t whole square. Okay, so that is basically 1 plus x square being approximated as 1 plus 2x for x being very less compared to 1. So binomial approximation. So this, okay. So now when you compare the two sides, you can first take out these two terms. Okay. And then you can see that with 2 delta t, you have terms like this. Alpha 2 L2 square minus alpha 1 L1 square by 4. Okay. So this will basically tell you that this term should be 0. It will tell you that this should be the case. So now we can substitute the values and find out alpha 1. Yeah, I'll do that. So finally, what is the value that we are getting? Alpha 2 was 6 into 10 raised power minus 6, and L1 and L2 was 16 and 12, right? So 6 into 10 raised power minus 6 into 4 L2 square, right? Sorry, L2 is 12 and L1 is 16. This is what I am getting for alpha 1. You can just check out my solution. Okay, so let me take you back to the basics here. So what we want is this situation, that the expansion of the two sides, which will tend to increase the h, versus the expansion of the base, which will tend to decrease the h, they should be balanced in such a way that even when expansion happens, the height remains unaltered. So this is the situation that we want. So that is expressed through equation 1 and 2, that this height h remains the same no matter how much we increase the temperature by. So for that to happen, this is the condition: comparison of equation 1 and 2 and equating the value of h in the 2. That is the condition. Okay, so hope this final solution is clear to all of you. Okay, very good. Now next thing we'll understand about thermal expansion, very important. Is the behavior of a cavity in a material with temperature change. Okay, so to understand this, let's visualize an example like this. Suppose we have a metallic sheet like this, which has a circular cavity in it, a round cavity in it, which is slightly to this side, the cavity is like this. So we'll discuss about three-dimensional bodies also, but here let's talk about a two-dimensional laminar surface. So this is a metallic sheet, okay, which is at T equal to T naught, it's like this, with a round cavity in it. So that cavity is of radius R naught. Okay. So the first question let's try to answer is that what happens to the radius of the cavity when the temperature increases? What should happen to this thing? Okay, the metal has coefficient of linear expansion alpha, and then we'll discuss few more things. Okay. Yes, very good. The radius of the cavity will increase. Okay, so the answer to this is that the radius of the cavity should increase. Okay, very good. That's correct. So the cavity's dimensions will increase such that any linear dimension will be alpha delta t. Any area dimension will be 2 times alpha delta t, and so on and so forth. Okay. So basically, when I increase the temperature here, so not only that, what we'll understand, what I want to explain here is that supposing we had 2 points A and B over here, and let's say we had another point C over here, and we had another point D over here. Okay. So the distance between each pair of points will also increase. So right now the distance between AB you can see is 1 diameter. So that will also increase according to the same law of thermal expansion. This fractional change is alpha delta T. So that is what shows you that the diameter or radius of the cavity should increase. Similarly, the distance between the points B and C, the chord length of the circle, that will also increase. The chord length of this circle AC, this will also increase. The distance between the points C and D, or the distance between the points A and B, any pair of points, now the distance between them will increase. Okay, so let us say L1 is the distance AB, which in this case is 2R0. And similarly, L2 is the distance, let's say AC. L3 is the distance BC. And L4 is the distance AD. And L5 is the distance BD. So all of these will increase when the temperature increases. And let's understand visually how that happens. Okay. So basically the whole metallic sheet with the cavity in it will expand in such a way that all these linear dimensions, not just the radius, the length L naught, the width B naught and all, but any linear dimension like this L1, L2, etc. that I've written on the side, all of these will expand according to the principle of linear expansion. So if this was the shape at this temperature, then at a new temperature, okay, so if this is the shape at this temperature, then at a new temperature, what should happen is that the whole body should expand in such a way that something like this occurs. Okay, the centering of the hole will change, because you see, if the the geometrical center of the original body was here, then later also the geometrical center of the original body, the so-called center of mass, should remain here. So compared to that, the center of the circle, if it was over here, this point O, let's say, now that would have gone somewhere here to this point O prime, because even this distance O prime C prime will be the original distance OC into 1 plus alpha delta T. So this is how the dimensions will look at a new temperature, T naught plus delta T. Okay, so L would have become L naught 1 plus alpha delta T. B would have become B naught 1 plus alpha delta T. But the radius also will expand according to the same principle. Okay, and all those quantities L1, L2, L3, etc. we had seen over there, they will all expand according to that principle. And so on and so forth. Okay, so the easy way to understand this is that a cavity will expand or contract on temperature rise or drop exactly the same way as the material removed to create the cavity. So understood the point now? The disc of metal that we have cut out to create this round cavity, the way it would have expanded under the circumstances, the round hole will expand in exactly the same way. Center will change, na beta, because the distance of the center of the hole, see, this is the point I'm trying to make, na, ki, suppose in my original metallic sheet without the cavity, this is the center of mass and I've just marked some point O over here. I've just, with a permanent marker or something, I've marked this point O. Now when the temperature increases, unless I'm applying any external force on it, the center of mass should remain stationary, but the whole body has expanded. Na? So this point would have moved this side, because it would have expanded in this manner. Na? You understanding this, Nikita? So as part of this, if I had a cavity here, now on increasing the temperature, the cavity will have to expand, but also the position where the cavity center was, that would change with respect to this, in this way. So that is the thing. Na? You just visualize that you have cut out a metallic disc from here. So how that metallic disc would have behaved in the original thing? Instead of a cavity, if you just colored this metallic disc here, so then that color would have expanded to this new position here. So just like that, that cavity will also behave. That is what this statement here means. If you just remember this statement, you will not have difficulty applying the concept in this type of question where there's a cavity involved. Yes, Ayush, weight remains constant. The density is the factor that changes. See, the amount of substance is not changing. No? So mass is not changing. And obviously we are on the surface of the earth. So gravitational field acceleration due to gravity is not changing. So weight is also not changing. Okay. Yeah, it can diagonally also move. It depends on how this position of the O is. No? If it is lying on the bisector, then the diagonal length will not change. I mean, it's only the. So, for example, if the center of the cavity is lying on this bisector, okay, then this round hole will move in this way. So after expansion, it would have gone, let's say, somewhere here. But if the center of the cavity is not lying on the bisector, the cavity center is somewhere here. Then on expansion, it will go somewhere here like this. So with respect to this, it's gone in this direction. Here, with respect to this center of mass, it has gone in this direction. You understanding the point, Amol? Okay. So, basically you just think like this, that instead of the cavity, if you did not have that cavity and you just made a, shape on the metallic surface. So you have this metallic surface, but let's say you drew with ink or something, wherever the cavity was and whatever the shape of the cavity, if you just put a paint this thing, patch over here, then when the thing expands because of temperature rise or when it compresses because of temperature rise, whatever happens, that patch of ink would also expand in a certain way. Okay. So now if you cut out that portion of metal and create a cavity of that shape, like that patch of ink, so the cavity shape, size and position will change just like that patch of ink's shape, size and position would have changed. So that is what that statement means, that any cavity behaves in exactly the same way like the material which has actually been removed to create the cavity. So that's like a universal statement. It applies whatever be the case. So the cavity will expand or contract with temperature rise or drop in exactly the same way that the material which has been removed to make the cavity. That would be it. Okay, so one of the consequences of this statement and this concept is that when we have a empty vessel, okay, like a glass cylinder, open cylinder of glass or something like that, the capacity of the vessel expands with temperature rise or contracts with temperature rise, just like a solid volume of that material would expand or contract. So a cylindrical open vessel of glass, its capacity will increase. By capacity, we mean the volume capacity. It will increase in exactly the same way that a solid cylinder of the same glass would expand or contract. Or if you look at the base area of the cylinder, it will expand or contract in the same way as a solid cylinder of glass's base area would. And same for the length. Okay. So the capacity of a container expands or contracts by the formula delta V by V is equal to gamma delta T, where gamma is the coefficient of volume expansion of the material of the walls of the container. Simple. No? So if, for example, we have a glass cylinder so we have an so its capacity is okay. So at a new temperature, its length would have become L naught 1 plus alpha delta T. Its radius would have become R naught 1 plus alpha T, where alpha is alpha of glass. So its capacity, okay, so if you calculate that, you'll see that is, so that is nothing but V naught. So you can see that delta V by V is gamma of glass into delta. Yeah, it is for the capacity. No? The volume that we're talking about is the capacity of the container because it's an empty open container. It's not a solid cylinder of glass. It's a hollow cylindrical shell of glass with a glass base. Now. So this is the capacity of the vessel. This is the capacity of the vessel. Yes. No, thickness will also increase, beta. हर चीज increase करेगा ना. So see, you can also visualize the cylinder like, I mean, cylindrical vessel like a solid glass cylinder from which another glass cylinder has been removed from inside. Okay. So all the dimensions increase now. So at a new temperature, it should become like this now. Understanding? So this radius is increasing, this length is increasing. So the capacity volume is increasing. Got it now? So basically this length, this volume that we are writing now is like the volume of the cavity that you have inside the glass. No? Like from a solid glass cylinder, you scooped out a cylindrical cavity. So uska capacity itna hai. So at a new temperature, the capacity of that container has become this much. So this will be according to this principle. Okay. So I've shown it to you by calculation here, but actually that was not required because you're just using the concept that the cavity will expand in the same way like the solid material that you removed to create it. So you removed a solid cylinder of glass of this much volume to create that cylindrical cavity, which is basically the capacity of the vessel. So that capacity will expand according to this formula. Okay. So for example, instead of this, if I had a solid cube of glass, okay, if I had a solid cube of glass and from that I have removed a hemispherical cavity at the top, then again the whole thing will expand in such a way that it satisfies that condition. The side view is like this. So again at a new temperature, this whole thing would expand in this kind of way. Okay. So this thickness, let's say, has become d prime. It was d earlier. And this radius has gone from r to r prime. Okay. This length has gone to l prime. So all these dimensions, they would behave in such a way. Okay, like this. So if you had a hemispherical cavity, okay, and this had a volume of 2 by 3 pi r naught cube at t equal to t naught. So this volume at the new temperature will become v naught 1 plus gamma delta t at t equal to t naught plus delta t, because that radius would become r naught 1 plus alpha delta t. So r cube become this. So that is nothing but gamma. Yeah, Vaishnavi, I'm scrolling now. So Amog, you have understood now. This was the part you wanted to note down. Okay. Yeah. So Vaishnavi, the next example is, suppose from a solid cube of glass or metal or whatever, I have scooped out a hemispherical hole like this, a hemispherical cavity at the top. So again, the capacity of that hemispherical cavity now, that will also expand according to the same formula. This cavity, it will expand according to this formula. So we don't have to do this manual calculation every time to understand. We should just understand that the shape of the cavity is a hemisphere. So that shape will expand in the same way like the solid hemisphere of whatever material we've removed to scoop out the cavity. Okay, so hope this is clear, people. Okay, very good. So based on this, we have one more formula, which is the formula for the apparent versus real.
Yeah, students, there is a power outage at my end, so my system is offline. Uh, just try to be online for a few minutes at least. Power should be back and should be able to resume within few minutes.
Okay, students, we're back online. Okay, just share the screen again. Yeah, so this is what we are going to discuss next: the real versus apparent coefficient of volume expansion as measured for a liquid. Okay, so the idea here is that when we measure the volume of a liquid in what is called a graduated container, okay, and then we increase the temperature of the system and re-measure the volume, and from that we calculate the coefficient of volume expansion gamma, then typically if we do not account for the fact that the container is also expanded, then we will get an incorrect value of gamma. We will get a wrong value of the measured value gamma. And how to understand the error in that? Okay, so by measuring the volume of a certain fluid in a container, okay, which you can think of as a graduated vessel, that means it has, you know, it can measure volume. Okay. The gamma for the liquid or fluid, whatever, can be calculated. Okay. So what's happening here is that if we suppose the vessel was calibrated at a certain temperature. Okay, so if the vessel is calibrated at T equal to T naught, okay, and a graduated container means it has, you know, the volume markings on the side, and the volume of liquid measures to be a certain value. Okay, so and V is equal to V naught for the fluid in the container at T equal to T naught. Okay. Now, when the temperature increases, if at T equal to T naught plus delta T, okay, the volume of fluid measured in the same container is V prime, suppose. Okay. Then find the relation in terms of the gamma of the fluid, okay, and the gamma of the glass, assuming it's a glass vessel. Okay. And from this, the apparent value of gamma, the apparent coefficient of volume expansion for the fluid. Okay, so what is the relationship between all these quantities? Let's try to understand this. Okay, so what will happen is that the fluid will expand, but the container will also expand. So like we discussed about the metallic scale last time. So what will happen is if your graduated container is accurate in measuring volume at the temperature T naught, because it is calibrated at that temperature, then at a higher temperature, it's going to give you an error. Now, because the graduations, the markings on the wall of the container, they will move further apart, and plus the base of the container would have expanded, so it will become inaccurate in its measurement of volume. So that's the first thing. Secondly, the liquid which is inside it, that is also expanded because of the temperature changing. So the actual liquid of volume has expanded. And secondly, the container has become inaccurate, because the container itself has also expanded. So both these factors put together will give you some new value of volume measured. And this value of volume measured, which I'm writing here as V prime, will not be accurate because you're measuring it using the same container, but at a new temperature. So the container has become inaccurate. It is giving you a certain percentage error because of its own expansion. Okay, so let's understand this question from that point of view now. So at t equal to t naught, what was happening? The least count, okay, of the vessel scale, you can say, will be 1 unit of volume, whatever that unit is. It might be milliliter, it might be liter, whatever. Okay, and the volume of liquid, okay, measured by it is x number of units. So V naught is x units. This is a true measurement. Okay, because it is calibrated, because the vessel was calibrated at t equal to t naught only. So that is why its least count was equal to 1 actual unit. Okay, now at the new temperature, you have to take care of two things. One is that the least count, this has become inaccurate. It has become 1 unit into 1 plus gamma of the glass into delta T. Okay. Whereas the actual volume of fluid, that has become V naught plus delta V naught. So that is into delta T. Okay. Now at this temperature, what is V prime? V prime is the measurement made by the vessel. Okay. So that's what I want you to find out now. Okay. So make sure you understand this concept, and I'm scrolling back to the question. So this is the type of calculation we are trying to do here. Okay, make sure you understand this first, then we'll come to the actual calculation. Yeah, so let's understand this. So what is happening is that at the original temperature, the least count of the measuring device is 1 unit of volume. No? So for example, the least count might be 1 milliliter. Okay. And the measurement that we are doing of the volume, X value, might come out to be, let's say, 50. So the actual volume of liquid is 50 milliliters. Okay. So suppose this is the situation. So this is the actual volume of fluid in the container at T equal to T naught. Okay. And let's say that T naught is 20 degrees C or whatever. Now let's say my new temperature is, let us say, 120 degrees C. So I've raised the temperature by 100 degrees C. Okay. And let's say that gamma of glass is, let's say, 2 into 10 raised power minus 6 per degree C. And gamma of liquid is, let us say, 1 into 10 raised power minus 5 per degree C. Okay. So then what is happening, that from this you'll understand that the least count has become 1 milliliter into 1 plus gamma of glass into delta T. So it has become 1 milliliter into this factor of 1 plus 2 into 10 raised power minus 4. Okay. So this is what the least count has become. Whereas the volume of liquid, the true volume, at this temperature, that has become how much? It has become V naught into 1 plus gamma of liquid into delta T. So that has become 50 into 1 plus 10 raised power minus 3 in milliliters. Okay. So the least count has gone wrong. It should have been, sorry, the least count should have been 1 milliliter for accurate measurement, but it has become this. And the volume has also expanded from V naught of 50 milliliters to this value now. It has expanded to this value. So what will be the new measurement? Okay. So the new measurement V prime will be the true volume of liquid, okay, at this new temperature, okay, divided by the least count, which is with error. It's not a correct least count because it is at T equal to T naught plus delta T. So if the new volume is some X prime units, that measured value of X prime units will be the true volume, which is V naught 1 plus gamma of liquid into delta T upon the expanded value of the least count, which is 1 unit into 1 plus gamma of glass into delta T, whatever the container is made of. So that X prime, the value of that measurement has become this. Understood? No? So that's why X prime will not be accurate. So here, if you do this practically, no, the measurement that we are getting now will not be actually 50.005. No, it will be less than that because the container is also expanded. Yeah, because see, Ayush, why the container's capacity, why the container's measurement least count will increase now? Because the container's base area has increased and the gap between the divisions on the vertical scale have also increased now. How is the container basically measuring volume? Because somebody has measured at the calibration temperature that the base area is so much. So that actual base area multiplied by a particular height, which is the height between two divisions, is equal to a certain volume. But at a new temperature, that calibration has gone wrong, no? Because the base area has also increased and the height between the two divisions has also increased. So that calibration has gone wrong by what factor? The same factor by which the capacity of the vessel has increased. No? That is the whole thing we're discussing about cavities and the way they expand. So now see what is happening to my measurement. So at a theoretical level, I will do this calculation like this, that my measured value x prime is the original volume, which was the true volume, into 1 plus gamma of liquid into delta T. And I can bring this term to the numerator by writing it as 1 plus gamma of glass into delta T to the power minus 1. And then I will use binomial approximation. So I'll bring this inside this power. So it will become V naught into 1 plus gamma of liquid delta T into 1 minus gamma of glass into delta T. And then I will expand this and neglect the fourth term, which has two product of two gammas. So this is actually 1 plus gamma of the liquid minus gamma of glass into delta T. Okay. So from the measurement, you would be concluding that x prime should be equal to x into 1 plus gamma into delta T. But this gamma that you're getting is the apparent gamma. It's not the true value. Okay. So from measurement, using that container, you're not getting the true value, because if you now compare this equation with this equation, you can see that gamma is equal to the actual gamma of the liquid minus the gamma of the glass. Okay, this is the apparent gamma. Okay, so same thing now I'm going to demonstrate with a numerical example. So in the numerical example, see what is happening is that the measured value, so at this temperature, the measured value that is going to be the true volume divided by the new least count. So the true volume was how much? It was this value, 50 into 1 plus 10 raised per minus 3. But the least count has become 1 milliliter into 1 plus 2 into 10 raised per minus 4. Okay, so the measured value is becoming 50 into 1 plus 0.001 into 1 plus 0.0002 to the power minus 1, which is approximately okay, which is approximately 50 into 1 plus 0.0098. Okay, so from this you can see that the apparent gamma is 0.0098. Okay, and delta t was 100. So the apparent gamma is how much? It is 9.8 into 10 raised per minus 4 divided by 100. So it is 9.8 into 10 raised per minus 6. So this is the apparent gamma. Whereas the true gamma of the liquid was how much? It was 1 into 10 raised per minus 5. So why you are getting that error? The true gamma of the liquid was this one here. But using this container, whatever measurement we are doing, we are getting the apparent gamma as little bit less than that. This is 10 into 10 raised per minus 6. This is 9.8 into 10 raised per minus 6. So we are getting a certain percentage error. So why that is happening is because when we are using the container to measure, the apparent gamma is actually the true gamma of the liquid minus the gamma of the glass of the container. So you can see that the measured value that we are getting, 9.8 into 10 raised per minus 6, is actually the difference of these two. नहीं 10 raised power minus 6 ही बेटा 9.8 है ना, it's not 0.098. I mean it's not 0.98. You can also write this as 0.98 into 10 raised power minus 5. So you can see here that is gamma is the actual gamma of the liquid minus the gamma of the glass. Oh, right, wait. There is some calculation thing here. It is not this. It's going to be 8 into 10 raised power minus 6, not 9.8. It's going to be 8. So we'll have to just check my calculation here. Yeah, my mistake. Okay. And delta T was 100. So the gamma apparent is becoming 8 into 10 raised power minus 6. Okay. Which is, by the way, this. It is the difference of these two. Okay, is the calculation all right now? X prime is the measured value ना बेटा. आप स्केल पे कितना मेजर कर रहे हो ना, वो x prime है. On this you are making a measurement na, the liquid is up to a certain level. So the mark on the side na, which division it is coinciding with, that is your x prime. But only that x prime is in milliliters na, because it's measuring volume. So x was the value of the measurement at the correct temperature T naught, and x prime is the value of the measurement at the higher temperature T naught plus delta T. So x was basically giving you the correct volume of V naught, but now x prime is giving you the false volume because your container, its least count has got an error now because it has expanded. So that's the important thing to understand here. Is it clear? So this, the value of this only na, is x prime. Its value of the volume, that only is x prime. Okay, good. So just now from this point, you can remember this as a formula. You know? The apparent value of gamma becomes the true value of gamma of the liquid minus the value of gamma of the material of the container. So if it's a metallic container, it will be gamma of liquid minus gamma of the metal, and so on and so forth. Okay. Now the last thing we will look at is the formula for bimetallic strip expansion. Okay. So when two strips of different metals, you have a lecture at 6. Okay, we'll take this up in the next lecture. Don't worry, it will just take 5-10 minutes. So next lecture we'll take this up, and after this we will get into this thing, calorimetry. Okay. Calorimetry is also a short topic, and after that we'll come to the main topic of kinetic theory of gases. So these are the topics coming out in the next lecture. Okay, this will have specific heat capacity, latent heat, okay, and the principle of calorimetry. Okay, so this is a very short thing, and then this is going to be the main thing. Okay, so that we'll discuss in the next lecture. So you can continue ahead for your next lecture. All the best, people. We'll take this up in the next week.